video we are going to talk more about the Suvat equations. So we introduced these equations in the first video. They're sometimes called the equations of motion. So they're used to describe the motion of a moving object. And in the first video we introduced a few examples of Suvat equations, and we talked about what the 5 variables involved are. So S, U, V, A and T, we defined them and we had a little closer look at them. In this video we're going to look at an example of a problem that you might get asked to solve using these equations. And because this is the first problem we're going to tackle involving a body in motion, a moving object, we're going to only consider it moving in one dimension, because that's the sort of easiest situation. Eventually you might tackle harder problems where the body is moving in 2 dimensions. So say if someone throws a javelin, it moves in an arc type motion. So it's not following a straight line, it's moving in a curve, which means it has a horizontal and a vertical element to its motion. But we're just going to think about things that are moving in a straight line, so they could be moving forwards or backwards along that line, but they're just moving in a straight line, so it's only one-dimensional motion. So let's look at the example. So a car is at point O, traveling in a straight line at 5 meters per second when the brakes are applied. The car comes to a stop at point A after 125 meters. So brakes are applied at point O, at which point the car is moving at 5 meters per second. 125 meters later, the car has come to a stop. So over that period, it's decelerating. So the questions are, A, what was the car's acceleration? So it's sort of implicit that it's got a constant acceleration over that point from O to A, over that period. We want to calculate that. And how long did the car take to stop? So we want to calculate the time the car took to come to a stop. So how long essentially did it take to go from O to A? So always with this kind of problem, draw a rough diagram. That'd be my first piece of advice, just to kind of get an idea of what's going on. It doesn't have to be accurate, it's just for you really. But it's good to draw a little sketch and then write down which variables, S, U, V, A and T, you already know and which ones you need to find out. So our diagram will look like this. We'll draw a line to represent the ground. We've got a point O, that's where the car is when it slams on its brakes. We've got the point A, and we know the difference between them is 125 meters. So that's the distance from O to A. So now we ask, which of the Suvat variables do we have and which don't we have? So do we have displacement S? Yes, because it's 125 meters. So by the way, if you don't know what S or U or V or A or T are, you should watch the previous video in the series because it's explained there. So displacement is 125 meters, and what we've done actually here in saying it's plus 125 meters is we've sort of defined a positive direction for our one-dimensional coordinate system, our axis. So from O, the origin, towards A, that's the positive direction, because that's the direction the car's moved in and it's got a positive displacement. So if a different car moved from O away from A, say it moved 20 meters from O in the direction away from A, so to the left of O, then it would have a displacement of minus 20, because relative to the origin it's gone down in the negative direction. But the car has positive displacement of 125, and what's its initial velocity? So that's U, well that's 5 meters per second, which again is positive because the car is moving in the positive direction as we just said. Its final velocity is 0 because the car has come to a stop. So we don't have to worry about signs here because it's just 0. The acceleration, well, we'll have to find that in part A, so we don't know it. And we don't know the time the car takes to do this movement because we'll have to find that in part B. So we now need to use the Suvat equations. So we have some variables and we don't have others, and we need to find them. So which equations are going to help us? So I'm not going to bring up all the equations because there's quite a few of them, but hopefully you have them in your notes or in some reference table that you are using, or you can Google them and find them that way if you need to, if you Google Suvat equations or equations of motion. So one of them, for example, is V equals U plus AT. So I might, if I was looking at all of them and I see this one, I'd look at it and I'd say, okay, can I use this one to solve part A? And the answer is no, because I have v and I have u, but I don't have a or t. I don't have acceleration or time. So I can't use this equation because I would have two unknowns. So this is no good, so I'll write down another one. V squared equals u squared plus 2as. So this one is good for solving A because it has acceleration in it. Part A is to find the acceleration. And then the other three things in it are v, u, and s, and I have v, u, and s. You can see I have those. So I can plug all the values in and then rearrange to get the acceleration, and then that's the answer. So let's do that. So we'll say that A, we start by plugging all the values we have into this second equation here. V squared, so v is 0. So I'm plugging in with their units. So the reason I plug in with the units is to show what the units of acceleration are. So I've not given acceleration A any units because I don't know what they are, but I've put everything else in with the units, and I treat the units as variables which I move around as I would anything else. So I've got v squared, which is 0 squared, so I square the unit, so it's 0 ms to the minus 1. So when I square it, I get 0 m squared s to the minus 2. That's v squared. And that equals u squared, which is 5 squared, so 25 m squared s to the minus 2 plus 2as. So that's 2 times a, and then s is 125 meters. So now I'm going to rearrange this so the 0 just disappears, we don't have to worry about that, and I'll take the 25 to the other side. I'll get minus 25 m squared s to the minus 2. And then with the 2 times a times 125 meters, I'll times the 2 by the 125 to get 250 times a. Now I take this 250 meters to the other side, so I divide by it and I get minus 25 n squared s to the minus 2 over 250 m equals a. Now we treat the units just like we would any other kind of variables or unknowns. So we have an m squared on the top and an m on the bottom, so we can cancel the m in the bottom with one of the m's in the top, and that just leaves m. And then we divide the minus 25 by the 250 to get a equals minus 0.1 ms to the minus 2. So we've cancelled, as I said, one of those m's cancels with the m in the bottom, and we just get m and then s to the minus 2. So that's exactly what we'd expect. The standard unit for acceleration is meters per second, or ms to the minus 2. So we've got the right units and we found it's minus 0.1. So the reason the acceleration is negative is because the car is moving in the positive direction, but it's slowing down. So whenever the car is moving in the positive direction but slowing down, it'll have a negative acceleration or a deceleration. If you like, you can think that the acceleration is working against it, it's slowing it down. So it's sort of working in the negative direction. If the car was moving in the negative direction, but slowing down, it would actually have a positive acceleration because the acceleration would again be working against it in the positive direction if the car was moving in the negative direction. So we have found the acceleration and we found it has a negative, which is exactly what we'd expect. We'd want a negative acceleration because the car is slowing down and moving in the positive direction. So great, that is the answer to part A. For part B, well, we want to find the time it takes to do this, and if we look at the first Suvat equation I wrote down, v equals u plus at, we have v, u, and we now have a, so we can use this equation to find the time. So we're going to plug into that. So we plug in v, u, and a into that equation, and we get v is 0, and I've plugged the units in again, so 0 ms to the minus 1 equals 5 ms to the minus 1, because that's u plus a times t. Remember, a we just found is minus 0.1 ms to the minus 2. We times that by t. So once again, the 0 just disappears, and we can take the 5 to the other side and get minus 5 ms to the minus 1 equals minus 0.1 ms to the minus 2 times t. We'll now divide the 0.1, we'll take that to the other side, so we get that t is equal to minus 5 ms to the minus 1 divided by minus 0.1 ms to the minus 2. Now you can see once again that the m's just cancel. There's an m on the top, m on the bottom, so they're going to cancel. The minus signs will cancel, so the answer is going to be positive. And you've got an s to the minus 1 on the top, s to the minus 2 on the bottom, so in total, remember you minus the power on the bottom from the one on the top, so you get minus 1 minus minus 2, which is 1, so you just get s. So we get 5 divided by 0.1, m's cancel, minuses cancel, and we're just going to have an s left, so that's 50s, so 5 over 0.1 is 50. So we're looking for a time, and we found that its units are in seconds, which is exactly what we'd expect, and we found that it took 50 seconds to come to a stop. And if you ever get a negative time, you've done something wrong. You've essentially said that the car moved backwards through time as it moved through space, which is not likely to happen. So always check that your time is positive. And so that is the final answer.
The music.